My infographic is on topic 8, probabilistic thinking. Probability is a measurement applied to events. It measures the chance of something happening relative to other possibilities. There are two ways to calculate probability: experimental and theoretical. Theoretical probability is only appropriate in situations where all outcomes are equally as likely. To begin finding theoretical probability, the equally likely outcomes must be counted. This can be done by listing the possible outcomes, drawing a tree diagram, and a two-way table. I prefer a two-way table as it ensures that no outcomes are missed and it is tidy and easy to read. To calculate experimental probability, we must collect data to make inferences about the different outcomes occurring. There are three ways to collect data, which are conducting an experiment, simulating the data, or using secondary data. I will now use this game as an example of how to calculate theoretical and experimental probability. In this game, I'll flip a coin and spin the wheel shuffle. The sections of this wheel are all equal in size, and a coin is the same material and density the whole way through, which means I can calculate a theoretical probability as all outcomes are equally as likely. I've used a tree diagram, a list, and a two-way table to find all the possible outcomes, which are heads 1, heads 2, heads 3, tails 1, tails 2, tails 3. When calculating the theoretical probability of an event, we divide the number of favourable outcomes by the number of possible outcomes. I've calculated the probability of flipping a head and spinning a 1. There are 6 possible outcomes to this event, and heads and 1 is only possible once. I divide 1 by 6, which equals 0.1667, rounded to the nearest 10,000th. To find the percentage, I then multiply this decimal by 100 to get 16.67%. As all outcomes are equally as possible, each outcome has a probability of 16.67. Next, I've calculated the theoretical probability of heads or 1. Looking back at my two-way table, I can see that heads is possible in 3 of the possible outcomes. 1 is possible in 2 of the outcomes, but if I've already flipped heads, then I've already won the game. So the number of favourable outcomes is 4, so 4 divided by 6 is 0.6667, rounded to the nearest 10,000th, and multiplying by 100 to find the percentage makes the probability of getting heads or 1 approximately 67%. To calculate experimental probability, I calculate my data in 2 ways. The first is I conduct an experiment by flipping a coin and spinning the wheel 20 times, and the results are in this table here. The second was using Excel to simulate the data 100 times, and the outcomes are in this table here. To calculate the experimental probability, we divide the number of times an outcome occurred by the number of times the outcome was possible, which is the number of times the experiment occurred. Here I've calculated the probability of hands and 1 for both the experiment and the simulated data, which in the manual data, it happened, heads and 1 occurred twice, and I did the experiment 20 times, so I divided 2 by 20, which equals 0.1. We had the same result in the simulated data. For heads or 1, I added up all the times that heads happened and all the times that 1 happened. So that was 2, 7, 2, and 4, and divided that by 20, which equaled 0.75. I did this again for the simulated data. I also calculated tails and 3 in this data here. I found that it's important when calculating both the experimental and theoretical probability to look at what the question is asking. The wording of the question greatly changes what is being asked. For example, heads and 1 had 2 results, while heads and 1, the manual data, had 15 results. Often the more time an experiment is done, the closer to the experimental probability will be to the theoretical data. If I had done the simulation 100 times, it may have been even closer. You can see here that 0.18 is a lot closer to 0.16 than 0.2 is. Calculating probability ties in with topic 3 of EDN114, thinking with fractions. When we calculate probability, we divide the number of favourable outcomes by the total number of possible outcomes. In other words, the whole, which is the number of possible outcomes, is divided by a proportion of the whole, the number of favourable outcomes. These divisions can be written as a fraction before being simplified or converted into a decimal or percentage. The fractions represent that the probability is an outcome of the proportion of the collection of all the possible outcomes in a situation. When probability is quantified, it is expressed as a number between 0 and 1, and can therefore be a point on a number line between 1 and 0. Fractions and decimals and percentages are numbers that have a point on a number line. Probability is often represented as a percentage. A percentage is a fraction that represents a part of a collection of 100. As probability is expressed as a number between 0 and 1, the decimal can be easily converted to a percentage by multiplying the decimal by 100, as you can see here on my example. In the example I've previously used, all the outcomes have been equally as likely. I will now go through two examples where the results are not equally as likely and the ways I would be able to calculate the experimental probability. With this spinner here, the sections are not equal, so we would not be able to use theoretical probability. I would have to either simulate the data using software or conduct an experiment to see how many times each outcome occurred to calculate the probability. In this example, I'm asking what's the probability of one of my students in my classes getting a band 4 in that plan. In this case, I wouldn't be able to use theoretical probability either. The best possible way to find the probability was be using secondary data sets to find the probability using relative frequency. Probability and topic 9, statistical thinking, are interconnected. They both look at real-life situations and questions. Probability uses statistics evidence to support the predictions made about the likelihood of an outcome occurring. You can see when I collected my data for the game in this example, the results are statistics I then used to calculate the likelihood of different outcomes. There are lots of misconceptions when it comes to probability, like saying I've had 3 heads in a row, so I'm due for a tails. That's a common misconception because probability of the next outcome is not affected by the outcomes beforehand.